So we're looking at graphs and their derivatives. And remember, derivatives helped us graph functions. And so we're going to review what was chapter 5 in our textbook. And so in this chapter, I'm just going to read through this. We have explored various concepts related to graphs of a function. So we looked at when graphs were increasing and decreasing. We found critical numbers, number C in the domain of f, for which either the derivative equals 0 or the derivative doesn't exist. Critical points whose x coordinates is a critical number C and whose y coordinate is f of C. Okay, so points, we just plugged it back in our x value. That was our critical number to find that y value. We looked at relative maxima and minima, together known as relative extrema. We looked at concavity of a graph. We looked at inflection points, and that's where our concavity changed. And we saw that the first and second derivative tests provide ways to locate relative extrema. The last section brings us all the concepts together. Also, we investigate two applications of the second derivative. We looked at acceleration, the second derivative of the position function, and, well, we didn't really look at this, but the point of diminishing return on an input-output graph. Okay, so the following below is just the rules that helped us figure out where things were increasing and decreasing. Basically, we just found our critical numbers. We tested values on each side of that critical number. If that interval where we tested a value, that derivative was greater than 0, that tells us our slope is positive, so it's increasing. If that derivative, we plugged in a number in one of those intervals in between our critical values and it was less than 0, it was decreasing. Equal to 0 is constant. That first derivative test, finding where things were increasing and decreasing, we could tell if we had a max or a min. So there had to be a stipulation that C is the critical number of f on that open interval AB. We have to know that f is continuous on that open interval AB and f is differentiable on AB, except possibly C. So we say that f of C is a relative min if we first have something which is the derivative greater than 0, so increasing on AC, and then after that we have something which is less than 0, which is meaning it's decreasing. So something that increases to decreasing, you can tell that this is a max. So we tell it's a min if we had something that was decreasing on one side of our critical value and then increasing on the other side. And this would be a min. So concavity kind of gave us the shape of the graph as it was increasing or decreasing. Oops. So to test for concavity, this is where we found the second derivative. We found values which set the second derivative equal to 0 or undefined, but was in our original domain. And then we looked at maybe not, if it was greater than or equal to 0, it was concave up. So remember, concave up could be either decreasing or it could look like this, increasing. And then if the double derivative on a side of a reflection point was less than 0, then it's concave down. Second derivative test was just another way that we could go about and find if our value, our critical number, was a max or a min, and it sometimes worked and it sometimes didn't work. And if this test didn't work, you had to go back to your other test. So suppose the double derivative exists on an open interval containing C, and that first derivative of that value C is equal to 0. So that's a critical number. If we plug that critical number back into the second derivative and it's greater than 0, then we can say that C, f of C, is a relative min. If we plug it back in, that critical number, into the second derivative and it's less than 0, then we can say that C is a relative max. If for some reason you plug that back into the second derivative and it's equal to 0, then it didn't tell us anything. That test was inconclusive and we had to go back to the other test. So we put all this together and we graphed. And so there were ways that we could graph, and these were just, and it didn't matter what order necessarily, but to help us graph a curve of a graph. A lot of times we should look at the domain of the function and know any restrictions. So we're going to avoid dividing by 0. So exclude any value of x, which sets the denominator 0. Taking the square root of a negative number, we got to avoid that, or any even root. Or taking a logarithm of 0 or a negative number, we got to exclude that. So those are things that we have to exclude when we're looking at our original function. It's helpful to find y-intercepts if they exist, and we can do that by plugging in 0 into f of x. Find any x-intercepts by solving for when f of x is 0, if that's not too difficult. We worked with rational functions at the beginning of the semester, so it's kind of bringing all this stuff together. At the rational function, then find vertical asymptotes by investigating the denominator when that's 0, and find horizontal asymptotes by finding the limit as x goes to infinity or negative infinity. If f is exponential, find horizontal asymptotes. If it's a logarithmic function, find vertical asymptotes. If you know about symmetry, it can be helpful to know that a graph is symmetrical across an x or a y axis, and that just tells us we have a point, then we know what another point is if it's symmetrical. So we can look at symmetry if we wanted to. F of negative x equals f of x. This is an even function, which means it's symmetrical across the y-axis. If f of negative x equals negative f of x, that's an odd function symmetrical with the origin. Okay. So we just determined our domain. We looked to see if it was rational. If it was, we looked to see if it had vertical asymptotes or horizontal asymptotes. Then we're going to look at where is our function increasing and decreasing. And so we can do that by finding the first derivative and locate our critical points, solving when our derivative is equal to 0, and determining where f prime of x does not exist, but our original function does. So find any relative extrema from where it's increasing or decreasing. Then once we've done the second derivative, or first derivative, we can find the second derivative to find any potential inflection points where it's changing concavity. And this is where our second derivative is equal to 0, and where our second derivative doesn't exist. So determine f is concave up or concave down. We're going to plug in our intervals into that second derivative. So plot your intercepts, critical points, inflection points, asymptotes, any other points needed. And then we're just going to connect things in a smooth manner and using the correct concavity. And it doesn't hurt if we have the technology available, we can check our graph with a graphing calculator, or we've been using Desmos in this class. And if it looks different than what you've drawn, see what the way that it differs to help us find the mistake. Okay, so let's put this all together in an example, or a couple examples. Okay, so the next example, actually all the work is kind of done for us. The derivative's been found, information about the graph has been found, and we are gonna graph a function with the properties listed. So we're given that we have a continuous function and it's differentiable everywhere except x equals -3, where there's a vertical asymptote. So because it's continuous everywhere and it's differentiable everywhere, I know that it's a smooth graph and there's no jumps, discontinuity or asymptotes, except for it told me at x equals -3. So it said I had a vertical asymptote here. So let's just do our dotted line at x equals -3 to denote that. And then looking at this, it tells us that we have a horizontal asymptote when y is 1. So looking at when y is 1, we have this horizontal asymptote in here. We have an x-intercept at -2. Let's plot that point. We have a y-intercept at 4. So let's put that point in here. We know that the graph is greater than 0, derivative is greater than 0, on the interval from -infinity to -3, and from -3 to 2. Okay, so let me just kind of put a note when I'm not sure I'm going to put this note. So we know that our first derivative is greater than 0. So that means that it is increasing. So I'm just going to put it's increasing here. I don't know if this is below or above the x-axis as it is, but I'm just going to put that it's increasing here. And we'll come back and we'll think about it later, the shape and where that should be. And we're given that from 2 to infinity, that our first derivative is less than 0. So from 2 to infinity, I know that this graph will be decreasing. Okay, so second derivative is greater than 0. That's telling us that it's concave up. So from -3, -infinity to -3, this is concave up. Well, it's increasing and it's concave up. So it's going to have this type of shape. Again, I'm not necessarily going to be below the x-axis here. I'm just putting in the shape. So that was from -3 to -infinity, and 4 to infinity. Notice 4, it's a decreasing function. So 4 to infinity, I know it's concave up, but it's decreasing. So it's going to have this type of a shape in here. I also know that because it's concave up here, and this is at 4, I probably have an inflection point. So we have an inflection point when x equals 4. And then we're told that it's concave down when the double derivative is less than 0. And that's on the interval from -3 to 4. Okay, so -3 to 4, it's concave down. So concave down, but we have things that are increasing and decreasing. So concave down has this shape. So it's increasing for a while, and then when we hit 2, notice that it was decreasing. So it's going to have a max there. And this is, again, I'm just doing the shape. That's not necessarily where it's at. I know that my first derivative at 2 is 0. Notice that that's where it was changing, increasing to decreasing. So this is going to be a local max. And it told me in the inflection point, which I told you we were going to have an inflection point at 4, but that value was at 4.3. So if that's the case, and I know I have a max at 2 and it's decreasing, I need that max to be above this 4, 3. So maybe right there. Okay, so we knew it was concave down. And we know that it's crossing the x-axis right here. So, and we have a vertical asymptote here. So it's going to look like this. We're going to continue concave down, concave down, concave down. We're going to hit our max, concave down, concave down, concave down. At 4, though, we're changing to concave up. Get rid of the pieces that we don't need anymore because we graphed it.
Professor, just a quick question. How did you get the very top dot?
Oh, yeah,
I was kind of confused on that. So,
it's okay. So this is where we were given that this was a derivative was equal to 0. And so I knew that that was a max value. It didn't matter how high it was, except that I know that it was increasing until I hit x equals 2 and then decreasing. And I had to hit this 0.43 because that was given to me. So
oh,
I just knew it had to fall above there somewhere.
oh, okay. Thank you so much.
You're welcome. And then the other piece that we don't have yet is this left-hand side of that vertical asymptote. We know that it's increasing and it's concave up. Notice that it didn't tell me it was crossing it didn't tell me I have an x-intercept on the left of -3. So I'm going to keep this above the x-axis. And I know I have a horizontal asymptote here. So I could be following that horizontal asymptote. It's increasing, it's concave up. And then I'm going to, vertical asymptotes we can never cross. Horizontals we can. And it's strictly increasing there. So we got that picture increasing concave up. So we kind of just put all the pieces together and graphed it. So in a way, and I was explaining it while I was doing it, so it took me a lot longer than it might have. In a way, this can be a good test question, the fact that it tells me that you know the stuff that we've been doing with derivatives, what it means, first derivative, second derivative, all of these things without having to go through and spend a lot of time finding all this information. Or it could be a great test question to go through where you're given this equation and you have to find all this information and then put it together. It also tests everything. So now let's look at an example where we have to graph this, putting all this information together. So we're given a function f of x is equal to x plus the fraction 8 all over x. And it's asking us to graph the function considering the domain, critical points, symmetry if we want, relative extrema, regions where the function is increasing or decreasing, inflection points, regions where the function is concave up, concave down, intercepts where possible, and asymptotes where applicable. So we can go ahead and start doing this now. Notice here for our domain, there's one value that we can't have for x. X cannot equal 0 because that would put a 0 in my denominator for that 8 over x. All the other values are in my domain. So basically negative infinity to 0, union is 0 to infinity. That would be my domain of this function. If I was looking for where my y-intercept is, might as well, just because this is right here. Well, that doesn't work, does it? because that would have given me I just did this up here, f of 0, undefined. Okay. So x-intercept, that is when y is equal to 0. And so we would have 0 is equal to x plus 8 over x. Well, let's clear our fraction. We can do that by multiplying both sides by our LCD, our denominator that we're trying to clear, which is x. So x times 0 gives us 0 is equal to x squared plus, distributing this, x cancels, we are left with 8. So if I take and get rid of the 8, put it on the other side, I can use my square root method, and I get x squared is -8. I notice right here when I use my square root method, I have plus or minus the square root of a negative number, which is not real. And so this is not a real number, it's imaginary, it is a number. And so this means it does not cross the x-axis. So it does not cross x-axis. Okay, so let's take the derivative, find where it's increasing and decreasing, or actually vertical asymptotes too. If we're going to look at a vertical asymptote, we have to make sure it doesn't set our numerator equals 0. Let's put this as a single rational function. So I'm just going to get a common denominator here just to find my asymptote. So this gives me f of x equals x squared plus 8 all over x. So notice 0 sets the numerator or denominator equal to 0, but not also the numerator. So I know I have a vertical asymptote at x equals 0. To me, though, it's easier to take the derivative almost of what we originally had. Let's look at our original function as x plus. And so instead of writing it as 8 over x, let's write it as 8 times x to the -1 power. So we want to find the first derivative. Derivative of x is 1 plus the derivative of x to the plus the derivative of 8x to the -1 is -1 times 8x to the -2 power. So our derivative, if you want to rewrite it, is 1 minus 8 over x squared. So we were looking at when is this equal to 0 and where is it undefined? So it's undefined again at 0. This cannot be a max or a min. If it comes increasing and decreasing, it's not a max because it's undefined there, or vice versa, decreasing to increasing. But we need to see what's happening on this side of the vertical asymptote, each side. And then our derivative is equal to 0. And 1 minus 8 over x squared equals 0. Again, we can clear our fraction. Multiply both sides by, in this case, x squared. We would get back x squared minus 8 equals 0. If we solve for x, this time we would add 8 to both sides, it's positive. So taking the square root plus or minus the square root of 8. Well, 8 is 4 times 2, so the same thing as plus or minus 2 root 2. Since I am graphing this, it helps me to know about what 2 root 2 is. So 2 times square root of 2 gives us back 2.8 about. Okay. So this is where we wanted to test our intervals. And so we had to put down our critical numbers. And so we had a negative 2.8. We have 0, and we have positive 2.8. So choose a number. And we're going to plug it into our first derivative.
Professor, I have a question.
Yeah.
I thought 0 was not in our domain.
It isn't in our domain, but because there's a vertical asymptote there,
Oh, okay.
it could be increasing or decreasing on each side, and it could change. So we
Okay.
have to put that in there. But good, great question.
Thank you.
And so let's test. And so let's say we put in x equals -3, anything to the left of -2.8. Just put it here. That's enough. So if I chose x equals 3, -3, and I plug that into my derivative, I get f prime of -3 is equal to 1 minus 8 all over -3 squared. Remember, we really only cared if this was positive or negative. This is 1 minus 8 over -3 quantity squared is positive 9. 8/9, that's smaller than 1. And so this is going to be equal to really 1/9, which is greater than 0. And so that tells me on the left of -2.8 or -2 root 2 that our function is increasing. And now choose something between -2.8 and 0. So if we chose x equals -1, and we went back in and plugged that in wherever we saw an x, we would get that this is equal to, into the first derivative, 1 minus 8 all over -1 squared. So this is 1 minus, well, -1 squared is 1, all over 8 is 8. So 1 minus 8 is -7, which is less than 0. So that tells me it's decreasing until I hit 0. And then choose +1 maybe. Same idea, this is where it's symmetrical. If you plug in +1, notice that you're going to square it, will give me the same thing. So because of symmetry, I know that this is also decreasing. And then if I plug in +3, same idea, I'm going to get the same number if I square -3 or square +3. So really, this is the same thing, plus or minus. And so that was a number bigger than 0, so it is increasing. So we can start putting together what we have. So we have this vertical asymptote on our y-axis. We didn't have any intercepts at -2. Root 2. We know that it's increasing until there and then decreasing. Okay, because this is an asymptote here, I can tell where my graph has to be. because it's never crossing my x-axis. So if I had something that was increasing, and then decreasing. Well, notice that that would work underneath the x-axis because of that, where that asymptote is. But if I put this above the x-axis, where it was increasing and then somewhere it's changing direction here and then decreasing, it would have to cross my x-axis, and that's impossible. So I know right now that this piece is going to be below the x-axis. I don't know about that concavity, and I don't know where that y value is, but I can find it really easily. So for now, let's just go up and down. And then we know it's decreasing on the other side of 0, x equals 0, or y-intercept, or y-axis. And then it's increasing at 2.8. And so again, if it's decreasing and then increasing, if it was below the x-axis, I would have the same problem as the other side. This would have to go and cross the x-axis, which I know it doesn't. So this piece has to be above the x-axis. And again, I don't know exactly where the y value is until I look for it. And I don't know concavity yet. But I got the general idea of where things are going to be. Remember, we can find out what our points are. So we're given that x equals -2 root 2 is where the max, where local max is. And if we plug that into our original function, that was equal to, we had x plus 8 over x. So x, so -2 root 2. Plus 8 all over -2 root 2. So -2 root 2. I notice that this simplifies a little bit. Negative, positive, this is negative. 2 goes into 8 4 times. This is 4 over root 2. I can rationalize my denominator by multiplying by root 2 over root 2. So I get -2 root 2 minus 4 root 2 all over 2. 2 goes into 4 twice. So this gives me, and we have like terms because we have the same radical with a radical underneath, a radicand, same radicand underneath. So -2 root 2 minus 2 root 2 is -4 root 2. Which gives us about -5.7. So we found that point where that max occurs. So -2 root 2, comma, -4 root 2. This point is kind of down, more down here then. Same sort of idea. We can see that it's decreasing and then increasing at 2 root 2. So let's plug that back in. So I have 2 root 2 plus 8 over 2 root 2. So this is 2 root 2 plus, if I rationalize the denominator, we were just doing that. We can reduce. We got back that that was 2 root 2. So this is at 4 root 2, which is approximately 5.7. So I'm just estimating. And this was decreasing to increasing. So min at 2 root 2, comma 4 root 2. Oops. Comma there. We're almost there. The last thing we need to do is find concavity. Concavity is with a second derivative. Let's take it from here. Let's see. Our first derivative we found was this. Our first derivative was equal to, and let's rewrite it, 1 minus 8 times x to the negative 2 power. So let's find the second derivative. So our second derivative, f double prime of x, derivative of x, a constant, I'm sorry, derivative of 1, a constant, is 0, minus 8, bring down our power, negative 2, subtract 1 from our power, which is a negative 3. So double derivative equals 16 all over x cubed. We want to see when this is equal to 0. And it's never equal to 0. If you clear your fraction by multiplying both sides by x cubed, you get 0 equals 16, which doesn't work. But it's undefined. At 0. And so it could be changing concavity on either side of that vertical asymptote that we had. And so we wanted to, again, test our values. If we chose something to the left, x equals negative 1, and plugged it into the second derivative, we get 16 all over negative 1 cubed, which is negative 16, and it's less than 0. So it's concave down here. And if we plug in positive 1, we get the double derivative of 1 is equal to 16 all over 1 cubed, which is greater than 0. So this is concave up. Let's go back to our picture of what we started. Concave down on the left, concave up on the right, which is basically what our picture looks like here, except that we have to make that shape now. So concave up, and then concave down. And this graph is actually symmetrical across this origin. It's an odd function. Okay, so we were able to graph this function by using techniques of derivatives to help us find this. And it put everything together from this chapter.